Okay, let's go over how you run closed population models in MARC. So I'm going to start a new project here using the mixed closed one data set. So I'll open that, I'll just say mixed closed one. And now crucial part here as we click on closed captures, and we'll start off with the full likelihood P and C, and then we'll add heterogeneity later. And the number of occasions in this case is 9. 1 they were captured, 0 they weren't, and the numbers are just the number of individuals in this simulated data set that had that capture history. And remember, this is set up ahead of time with a to simulate a population that had 2 mixtures, no behavior, and no time effect in capture probabilities. So we know where we're headed, but we're going to run all the models just to see how they work out. Okay, if we hit OK, first thing to take a look at are the the PIM matrices. So let's just look at them all. I'll tile them so you can see them a little better. So you just have one row for the P's and C's, and then one value for F sub O, just one estimate of F sub O for the entire population. And remember, the subsequent rows on the Cormack-Jolly-Sieber models had to do with different cohorts that were joining the population over time. We don't have any new cohorts joining, or assuming we don't, because we have a closed population with no individuals coming or going. And so if we look at this using the chart, the initial model that it'll give us is estimating different value for P across every time step, different value for C across every time step, and then F of O. Remember, this is a nonsensical model in terms of closed populations because we have to constrain that last P, or we can't estimate F sub O. Take a look at the MARC book. If that doesn't make sense, we can run this knowing that this doesn't make sense, but there can be some learning opportunities here. And we'll just look at the PTs and the CTs after it runs, show you what's going on. So here we go, we've got our model, but if we look at our output of real parameters, a couple things you'll notice is that last P is set equal to 1, and as a result, F of O is essentially 0. So the estimate of population size that you get is just total number of different individuals that were captured over the period. So not what we want, but we can easily modify the PIM to give us a model that does make sense, and this would be that first one. And this would be model M sub T, okay? So now, look over here, we have the P's and the C's. First row is a P, second row is a C's, and we've set the C's equal to the P's. So remember, C is recapture probability. That's the probability of being captured after you've been caught once, and that recapture probability then stays the same. You're either trap happy or trap shy. And there's going to be one fewer parameter for C than for P because you can't have any recaptures on that first occasion. And then we just have the one block for F sub 0. So if we run this, this would be, in terms of our longer notation, this would be F sub O PT equals CT, which, as we said, is equal to model M sub T in the Otis. And we run that, and interestingly, it doesn't do as well as that top model. But if we look at the parameters, you see that you do get an estimate for F sub O, pretty small, and no problem with the P's. All the P's are estimated. We could take a look at the N hat. We know the true population size is 2,000, so this isn't doing so well. It's not coming even close to overlapping 2,000. Very small standard error, so we think we've got a good estimate, but we really don't. Okay, so let's modify this some more to come up with some other of our favorite models. So I'm going to make the C constant. So by clicking on that rectangle, right-clicking, and then hitting constant. So now setting P constant and C constant, and we still have our F sub O. So this would be equivalent to the behavioral model. We have one estimate for initial capture probability, P, another estimate for recapture probability, and then, of course, F sub O. So all we have to do here is say we are going to change this. Instead of PT and CT, it's P dot, and they are not equal. They are allowed to be different, but still very constrained. We just have 3 parameters here. We say, yeah, we'll do identity matrix, yes, and now this is coming up a little bit better. Still not as good as that first nonsensical model. Both these cases, it's warning us that the number of parameters might not be right. But if we look at this, 3 parameters, yes, that makes sense. 1 for P, 1 for C, and 1 for F of O. And the same here, we have 9 estimates of P plus 1 for F sub O, so that all makes sense. So let's run our last and simplest model, where we just make P and C equal to one another, and then we have our F sub O, so we just have 2 parameters. And I'm going to run that, and all I have to do now is say P dot is equal to C dot. So no difference between initial and subsequent capture probabilities. Yeah, add it, yes, close, and see that doesn't do quite as well as the behavior model. But again, getting all these warnings on parameters except for this one, and they all look good. So just to show you how you can run all of these using the design matrix approach, we've run the 3 models, M sub O, M sub T, and M sub B, and we can have Mark build those for us, and in that case they'll use a design matrix. So these AICs and deviances and so on should be the same. So this is model MB, where we have a separate P and a separate T, and that matches the model built using the predefined models. Next is the M sub T, sorry, M sub O, where we have P is equal to C and only 2 parameters, yeah, and then M sub T, where we have PT equals CT, and that's the same. So if we just look at design matrix from this last one, you'll see that it looks similar to design matrices that we've run for the Cormack-Jolly-Sieber. One intercept for P, and then each of these columns corresponding to the different capture occasions up until 8, and then 9 is probabilities defined by this last row. And then C, notice that the values, the identity matrix is matches the identity matrix for the P's, but we don't have a 1 for the initial occasion for C because we can't have recaptures. Okay, so just showing you how that all works. And if we look at Our estimates from this model M sub t, we should get the same estimates as we got for one we did with the PIM. That all looks the same. Okay. All right, so let's move on now to the heterogeneity model. And to do that, we go to PIM and change data type. And notice that we could do two different types with heterogeneity pi and p, and heterogeneity pi p and c. I'm going to choose that last one. You could choose that first one if you just didn't even want to consider models that have behavioral variation. It simplifies things a bit, but we will go ahead and go with the more complex. And now if we look at our parameter index matrix, we have a pi parameter, 18 estimates for P, because you have two mixtures, right? So 1 through 9, or I'm sorry, 2 through 10 would correspond to mixture A, and 11 through 19 would correspond to mixture B. And you have the same thing going on with your C's, but you have one fewer, okay? So 8 and 8. And then we have our one for F sub 0. So let's just go right to the PIM matrix to build our simplest heterogeneity model. So we're just going to look at the effects of heterogeneity on the capture estimate, okay? And now I have to close this to see those windows. I'm going to go to tile. And of course, this has, you know, all the way up to 36 parameters. And we are going to greatly simplify that. We're going to make it only 4. So I'm going to start with the P's, because if you look in the mark book, what we want to do is make a parameter matrix for P with all 2's across the top. So that would be the capture probability for mixture A, and all 3's across the bottom. That would be the capture probability for mixture B, and then that will be repeated on the C matrix, because we're going to make C's equals to P's. So the quickest way to do this is say initial constant. So now I've got everything as a 2 here, and I want to change this bottom row to 3's. And I got to check this because it's easy to make a mistake when you're doing that. And now I'm going to use this again. I'm going to copy a PIM to one or more PIMs. So I'm going to copy the P PIM to the C PIM. So I'm going to say select the one to copy is the P, and where to paste it is the C. And okay, this is what happens. For some reason, it puts a 2 in here, and I did this before, and I couldn't figure out what was going on for a while. So just be careful. This is part of the reason I'm just sticking with the running the design matrix and the predefined models with these closed population estimators. But this should be set up now. Oops. For the model M sub H. So we have one estimate for pi, proportion of individuals that are in mixture A, and then we have capture probability for initial captures, separate capture probability for mixture A, capture probability for mixture B, and we make that the same on the C matrix because we're not looking for any behavioral effects. So now if we run the current model, and I'm going to call this pi, comma, PA dot is equal to CA dot. So that's saying we're just one capture probability for all of mixture A, and then we have PB dot is equal to CB, CB dot, and then FO. Okay. So we'll have a capture probability for mixture A, capture probability for mixture B, no behavior effect. Should give us 4 parameters. Cross our fingers, say yes, and we add this to our list, and this goes right up to the top because by a lot, okay, 1,700 AIC units between this and the next ones, and that's because we know that the simulated data were set up to match that model. Okay, so now let's just go in and run the predefined models with the heterogeneity. So I'm going to run MH2. I'll run the, I'll just run everything with heterogeneity so we can kind of see how these all work out. And the main thing is MH2 should match this model that we've already run using the PIM, and in fact it does. Okay, so that's good. And if we just take a look at these estimates, now you'll see that we have this estimate for pi. So this 0.6067 is our estimate of the proportion of individuals that fall into mixture A, and this is the capture probability associated with them. And then, of course, that'll be the same for all the time periods. And then we have the capture probabilities associated with mixture B, same for all time periods. The C's and the all of the C's are going to be equal to the P's because we made it that way. And then here's our F sub O, the number of animals that weren't captured. Now let's take a look at this using the PIM approach. And one thing you'll notice right off the bat is that, of course, there's many fewer parameters to look at because this just reduces it to the number that you provide, okay? But notice here, pi is equal to 0.39326, okay? It's like, whoa, pi is equal to 0.6067. It turns out that these are just 0.3932 is just 1 minus 0.6067. You can confirm that. So this is giving us, the other group is the measure of pi, and then you see that the first P that we get is 0.2499, same as the P that we get for mixture B here. So we've just flipped the mixtures A's and B's, so that flips the P's, but everything is exactly the same. Otherwise, we get the same value for F sub O, and we should get the same values for estimate of overall population size as well. If we do our derived estimator, 1995 for the PIM model and 1995 for the model made using the design matrix. So everything's working out the way we think, but the pies are flipped. Okay, if we look at model MBH2, so now we're adding the behavioral effect. So now we have our two mixtures. Our pi is about the same as we saw before. The initial and or the mixture A and mixture B capture probabilities are about the same as we saw for the previous model. And now we have the behavior effect, but notice that it's almost exactly the same as the capture probability for initial capture. So that's just showing us that there really is no behavior effect going on in these data. And that's reflected in those values of P's and C's. They're really not differing. MTBH2, now we're just allowing things to vary over time for each period. So here are the capture probabilities for mixture A, capture probabilities for mixture B. And you can see they're considerably lower, but they vary up and down in the same way because it's an additive model. Then again, we really don't have much difference with the C's. Obviously we're adding a lot more complexity to the model, but not really getting any better estimates. So one last thing to show you here is the random effects model. And again, we'll have to change the data type and we'll run the Huggins PNC with random effects. So now we can't compare the AIC values, right? Because we're going from the full likelihood to the Huggins, which conditions out F sub O. So I'll click OK, and then I'm going to run, predefined models here, and I'm just going to run M sub O RE, so random effects, M sub D RE. We know that the B's are really not adding anything, so let's just run these two. These take a little bit longer to run because now you have individual, you're trying to estimate individual heterogeneity. So here we got the M sub O RE. It's going to take a little bit longer to get the M sub T RE. If we look at this first one, and just take a look at these AIC values, okay? 21,948 versus, minus 3,687. That should tell you right off the bat, don't compare those AICs. If we look at our estimates from this, first off, we get this estimate of sigma P, okay, variation in P, and then we get one value, one overall estimate for capture probability. So this is saying that on average, capture probability is about 55% for animals in the population, but we have a spread of capture probabilities around that with a sigma equal to 1.31. Okay, that really doesn't tell us much about this model and how it compares to the model with the two mixtures, but if we look at our estimate of N hat, remember we did we were right on the money with the previous model that we looked at. And we are close, but not nearly as precise with the random effects model. Okay, so this is the estimate with random effects, 2031, bigger standard error of 14, lower confidence interval of 2007, so it does not overlap our true estimate versus the estimate using the heterogeneity model, which of course does a very good job. So just kind of showing you the different ways you can run these closed population models. So hopefully that helped you get going on your way.